I just thought I'd talk a little bit about my journey through medical imaging, and I've been around for quite a while now. And it started in 1970 when I joined the electrical engineering department at Canada University, and encountered a cantankerous. Well, he seemed like old at the time. He was only 40, but he was an incredible mentor, and he was bringing Canterbury engineering into a new domain by starting to talk to people at the hospital. Electrical engineering had been just that up until that point, but he started talking to physicians, to endocrinologists, and he thought that we could use engineering principles to understand physiological processes in the body, in particular to look at the metabolic modeling that could describe how osteoporosis formed. And because osteoporosis and the endocrine function were closely related, he recruited a couple of grad students to do the mathematical modeling, but then he needed someone to do the imaging so that we could track osteoporosis in bone over time. So this is, and this is a 40-year-old. I remember him coming into the lecture room in a very cantankerous mood one day and threw chalk at someone at the back of the room and said, "I'm in a bad mood. It's my 40th birthday." Anyway, he asked me to figure out a way of measuring bone density in the forearm, and then said in the next breath, "I also want you to study scattering of radio waves in an inhomogeneous medium." I didn't even know what that meant at the time, and I didn't know what the relevance would be. And whatever you do, don't forget to use the Fourier transform. Some of you know what the Fourier transform is all about and how wonderful it is. I should just briefly mention what Professor Bates's interests were, which shows how eclectic he was on his outlook. He was interested in optical and radio astronomy, radio antenna theory, electromagnetic propagation, crystallography, physiological modeling, medical imaging in the broad sense. And all of these use the Fourier transform in some way. And then you've got in music theory, chess playing theory, and Gilbert and Sullivan. Yeah. An interesting sideline was when I was, I think just after I graduated with my doctorate, Richard challenged the Crick and Watson with respect to the structure of the double helix, because he had seen these crystallography diffraction patterns. And although this is what the double helix produces, also the side-by-side model, you can think of, instead of the double helix, you can think of the molecules being arranged more like a zipper, which made a lot more sense to me, because when you have molecules twisted around each other, pulling them apart, they should get tangled up. Whereas if they were side by side, you could pull them apart just like a zipper. And these two structures have exactly the same diffraction pattern. So he and a chemist friend spent quite a lot of time looking at the mathematics behind both of these. And they actually caused Crick and Watson to go back to their original work and do some more work. And it finally turned out that the helical model was in fact correct. But up to that point, there was really no way of differentiating between one and the other. So I started off in electromagnetic scattering and got thrown into a world of these sorts of equations, horrible looking stuff. And I really didn't, I couldn't get traction on this at all. It was far too much math. I had no idea who was going to use it. I had no idea how you would validate it. In fact, I remember one of my colleagues in EE at the time working in this field, and he gave a thesis presentation, and someone asked him, "Okay, you've done all this work. How do you know that your result at the end is correct? Because you haven't done any validation." He said, "I started off with Maxwell's equations and I didn't make any mistakes." So ultrasound and bone density. Theory was that if we had an ultrasound beam going through the bone, where there was less dense trabecular bone, the ultrasound beam would take longer to get to the transducer. If it was more compact bone, it would get there more quickly. And so we would have the transducer and receiver scanning across the bone and producing some sort of profile. But the problem is that ultrasound doesn't travel in straight lines. Most of it gets reflected by the bone, so there's very little left. And we had to build our own equipment anyway because there was no commercial ultrasound scanners available at the time. But I did know that if you took an X-ray of the bone, you get a nice picture of the bones. You got white where it was dense, you got black, dark gray when it was less dense, and you got black when it was just going through air. So I figured that if we can start off with that and we can take a bunch of pictures around the arm with these X-ray projections, maybe there's enough information in those projections from all of the directions to reconstruct the cross-section. So ultrasound versus X-rays, we came down heavily in favor of X-rays. So how do we reconstruct the cross-sections from X-ray projections? Well, we're highly motivated by work that had been going on even 10 or 15 years earlier in Australia with radio astronomy interferometry. And followed by the name of Ron Bracewell, whom, in my opinion, should have won the Nobel Prize for CT, was working with radio telescopes on a very long baseline and looking at the interference patterns from a radio source in the sky and trying to reconstruct those radio sources by analyzing these interferograms as the Earth rotated with respect to the stellar environment. And so he would take these interferograms that would change in angle as the Earth moved. This interferogram turned out to be the Fourier transform of the distribution he was looking at. And by taking multiple projections, building up the two-dimensional Fourier transform, he would come up with this reconstructed distribution in the sky. This turned out to be very similar to the problem that we were having with our bone scanning. We took projections, took the Fourier transforms over them, so the projection like this, take the Fourier transform, put it in this 2D Fourier space, build up the 2D Fourier transform by multiple angles, then we could do the inverse Fourier transform and get this image back. And so that's the approach that we started taking. This is the fundamental equation for CT, and by performing these operations in different orders, you can get a bunch of different kinds of algorithms, some of which have more practicality than others. So I won't go into which ones were used mostly, but we came down on this so-called back projection approach that was that led for very quick image reconstructions. If we look at what happens if we just take these projections and back project them over plane, we get a very, very blurred image. So if we just take each of these projections and back project those profiles onto a plane, we get some sort of reconstruction, but it's very blurred. And it turns out that blurring is this convolution function, 1 upon R. So if we replace every point in this image by a function that looks like 1 upon radius, it blurs out the image. But if we spatially filter this image by performing an inverse spatial filtering operation that has in frequency space this mod rho function, which means that we're amplifying the high frequency components, we're attenuating the low frequency components, we'll end up with a procedure that exactly compensates for this blurring function. I'm skipping through this very quickly, but the point is that we modify this projection by increasing its spatial frequencies, giving it a much more jagged look. But when we back project onto a plane, we get the full image reconstructed. So we used this approach, and we wrote our first paper on it in 1971 in the New Zealand Journal of Science. It's a very prestigious journal. We were using mathematical phantoms at the time, and we were expanding Bracewell's work in medical imaging to demonstrate the Fourier-based method for reconstructing objects from projections. The next step was, of course, to use a real object, and being in New Zealand, the obvious object was a sheep's bone. So we took a sheep's bone. This was the actual cross-section of the sheep's bone. And after we took 20 radiographs, made densitometer scans of particular line in each radiograph, transcribed these data from the curves onto punch cards, and it took 20 minutes to reconstruct a 128 by 128 image on an IBM 360 computer, which is what the university had at the time. It had 64K of memory and 1 megabyte of disk.
Now that would be a split second.
Yeah, well, we'll get onto that. We took this image, this reconstructed image, along to the local radiologists at the Christchurch Hospital, and basically patted this on the head and said, "Oh, pretty pictures, but we've got X-rays. We don't need these things. These cross sections. Who needs them?" And right at that time, Hounsfield came out with a news report in one of the science magazines, many science magazines, in fact, where he produced this. He showed this first EMI, Mark 1 EMI CT scan. Of course, Hounsfield went on to win the Nobel Prize along with Cormack a few years later. So in 1974, I completed my PhD thesis. I got over the temptation to give up everything and start a new career, but I kept going. It turned out that my thesis was the first PhD thesis ever to be written on CT. And then I began a job at Christchurch Hospital as a biomedical engineer and medical physicist. And somehow, I have no idea how I managed to do it, but convinced them to fund the development of our own local CT scanner. So the first prototype looked like this: X-ray tube, xenon ionization chamber, rando phantom that's commonly used for radiotherapy, machine calibration. So instead of the X-ray tube and detector rotating around the patient, in this lab setup, the patient rotated in between the X-ray tube and the ionization chamber detector. And so the first reconstruction we got looked like this, pretty horrible. And I thought, what's going on here? And then we realized that when you make an ionization chamber with a number of different detectors, you can't rely on every detector having exactly the same sensitivity. So we just had to come up with a calibration routine. And by the time we figured out that calibration procedure, we ended up with getting half decent images. And this is a cross section of that rando phantom showing the lungs and the spine and the heart. And a few years later, we had turned this bench prototype into an operational clinical prototype, where we had taken the motor drive of an old cobalt therapy machine that had been decommissioned. So we got rid of the cobalt bomb, but we left the motor drive, this thing you can see at the back, built an aluminium framework for the detector down here and the X-ray tube up here, and we ended up with half decent reconstruction. So pretty low resolution, but for radiotherapy treatment planning, they were just perfect. They're so much better than what we had available to us already. And all this was done for $20,000, which was pretty remarkable. Mind you, that's probably a couple of $100,000 in today's money. But even to get the hospital to come up with that money, a public hospital to come up with that money to help us was amazing. But a seminal day in my life that kind of changed the direction of my career happened in 1975. I was in the process of evaluating CT for the New Zealand government, and I was responsible for selecting CT that originally went into Auckland. I think the first two, Auckland and Dunedin, were the same brand of CT. But part of this was sending me to an international CT conference at Stanford University, your old stomping ground. This was also the time I was first exposed to MRI. It was a fellow who ultimately got the Nobel Prize for MRI, Paul Lauterbach, talking about a technique called zergmatography. How long since you've heard that term?
Gosh, I haven't heard that for years.
And his research would put objects into magnets and use these things called magnetic field gradients, which would make the magnetic field stronger at one end than the other. And by rotating these field gradients, he would be able to reconstruct an object that looked like that into these two blobs. A lot of people in the audience sort of scratched their head and said, you must be at the wrong conference, this is about CT. But then the penny dropped, was using the same sort of projection principles in CT, but we were getting them using magnets as well. So even though the data were acquired in a completely different way, the same algorithms could be used to reconstruct the images. But the other thing that happened at this meeting is I met a fellow by the name of Chris Thompson, and also a Kiwi, who was also from the same town as me. I met him at the cocktail party after this meeting. This room was full of guys speaking American, but there was some accent I could sort of vaguely recognize at the other side of the room. So I wandered across to him and said, "G'day, you must be from New Zealand." And he said, "Yeah, where are you from?" And I said, "I'm from Dunedin, so am I. Do you know this person, that person?" We had all these people we knew in common. And he had just moved to the Montreal Neurological Institute a few years earlier. And he was working with the very first EMI scanners in North America. So he quickly thought, well, perhaps we should get Terry over to M&I for a couple of years. And it sounded like a great idea. I didn't know that my French was up to it, but I eventually decided that we would go. And so 3 years later, with 3 kids in tow, moved to Montreal. So that started in 78. And in Montreal, Chris Thompson had been working with the very early PET scanners. And so they had been working with a group at upstate New York somewhere. I've just forgotten the name, Brookhaven. And his scanners could produce images like this. This is a brain tumor. And he was very proud of this string diagram that he constructed to show the reconstruction principles. Another thing he was working on was stereotactic image-guided neurosurgery. So we would use maps from neurosurgical atlases in conjunction with a stereotactic frame to identify whereabouts in the brain various electrode positions would be required to either stimulate the brain or record signals from deep within the brain, either to diagnose epilepsy or to treat Parkinson's disease. So while I was in Montreal, I also got working on reconstruction algorithms for PET. And over the years, Chris and I worked together to develop a number of rapid reconstruction algorithms so that the PET scan images could be reconstructed quite quickly. Back then, the computer we had was a PDP-11. I don't know if you ever remember a PDP-11. It was the best small computer you could buy, and it was in every imaging lab, pretty much every science lab in the world at the time. This was about 10 years before PCs became ubiquitous. And so we got involved in reconstruction for a bunch of different flavors of PET scans, getting higher and higher resolution, higher and higher sensitivity, until we could get images that could be registered with CT scans so that you could see the physiology, the function, and you could see the anatomy in the CT scan. So when I arrived in Montreal, we worked with the EMI Mark 1 CT scanner and the EMI 5005 CT scanner, which was the next generation up that could do body scans as well as head scans. And these provided three-dimensional, the ability to do three-dimensional imaging if you stack these slices up. But strangely enough, we already the people at Montreal were already very familiar with 3D imaging. They had this very sophisticated angiographic machine, which would rotate around the patient to get different views, but it had 4 X-ray tubes and 4 detectors. And these detectors weren't electronic detectors, they were film detectors. And the films had to change every half a second mechanically. So you would have two X-ray tubes producing a stereoscopic image from one view, two X-ray tubes producing a stereoscopic image from another view, and these things would clatter like crazy. Clack, 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 clack over 15 seconds as you injected the dye into the vascular system. You get all of these stereoscopic images. And so this was the way that the radiologists would view the stereoscopic images. They would put one on this light box, one on this light box, and look at them with these mirrors. Eventually, around 83, we ended up with an electronic digital stereoscopic angiographic system, so that we no longer had to have this very cumbersome mechanical device, but the images could be acquired electronically, and they could be acquired with left and right views, both from the same X-ray tube. So basically a flying spot that moved between two different locations on the anode of the X-ray tube. In 1984, MRI showed up. I had the same sort of reaction with MRI that some of our radiologists had with CT. The radiologists who were now very, very familiar with CT thought, what the hell do we need magnets for? We've got CT. Why do we need MRI? Anyway, it was not the radiologist I was working with, but the neurosurgeon who was the head of the institute that really got excited about MRI. So he engaged me to go through the same sort of process that we'd gone through for CT in New Zealand to go through for MRI in Montreal. And we ended up with a Philips MRI scanner. It was a so-called high field machine. High field was 0.5 Tesla at the time, but it was the first cryomagnet in Canada. And with the new MR scanner, we needed a new building. So I got involved in the planning of all of the infrastructure for the new MR scanner in Montreal. They had some anxious moments. The building was put up. We built it for the specs that we had for the size of the MR scanner. And then the scanner showed up, and you can see it was pretty tight. There was literally 5 millimeters space. This was the window of my eventual office, actually. So that was a great sigh of relief. Bill Findell, the director of the institute, was the first patient. Couldn't understand what the banging was going on. Is there something wrong with that? And of course, I also experienced what I hope you never have to experience, was a quench. In fact, we had a couple of these quenches.
We had a quench for ours.
Yeah.
Yeah, Wessel's being ramped up.
Yeah. Our 70 in London quenched about September. It's not back up in field yet.
Oh, okay.
Well, I think it got up to field yesterday, but they're going to take another 3 weeks to shim it and test it. Yeah, nasty problem when the magnet uses its semiconducting. Yeah. Yeah. So quench means when the very, very cold coolant in the magnet has got to be cooled to almost absolute zero. And if that coolant suddenly escapes, the magnet, the windings heat up and it no longer becomes superconducting. And so there's no magnetic field left. But in the process, it boils off hundreds of thousands of liters of liquid helium and liquid nitrogen, which fills the room and causes all of the moisture in the room to start raining down, and actually you get liquid oxygen raining to the floor.
It costs $100,000. Yes.
Well, it can cost, the 7T has cost about $2 million to bring it back up the field.
Right.
But the big advantage of MRI was for image-guided neurosurgery, and particularly stereotactic surgery. So the stereotactic surgery, we put a frame on the patient during imaging. This frame has these Z or N-shaped bars which show up in images. And by looking at where these points are in the image, we can mathematically say exactly where this point is with respect to this, the coordinate system in this frame. And so we can go directly to a specified target deep within the brain. Another cool thing that we did was integrating the Stereo DSA that I mentioned, the stereo angiography system. So this is just showing one view, but if there are in fact two views, that one for left eye, one for right eye. And when you look at these with stereo glasses on, you see the vascular system sort of looking like it's wrapped around the rugby ball. And the importance of fusing the vascular structures with the MRI is that if you want to target a point deep within the brain on the MRI, you want to make sure that you go through a vascular-free region. And by showing the surgeon the three-dimensional structure, three-dimensional formation of the vessels, both in the lateral and the AP views, we can make sure that they got to the target in very, very safely without penetrating any vessels. We also worked on stereotactic radiosurgery, where we are performing a very similar process to radiotherapy, but instead of multiple fractions spanning over 6 weeks, all of the dose would be delivered in one fraction. And so you're actually burning out the region rather than just hitting the cells that are replicating. And so this was a project that was done with the radiation therapy department in the Royal Victoria Hospital up the road. And one of the research projects, once 3D MRI had become quite well established, and you can see now we've got same resolution in all three directions, and this took a long time to get to this point, but eventually we were able to get 1 millimeter in XY and 1 millimeter between slices. And so we built up this so-called Viper platform for helping the neurosurgeons locate structures in the brain, like the thalamus and the globus pallidus, for there's targets for electrode placement. And this became the Viper platform. And I went back to M&I a couple of years ago, and the Viper pit, the Trou de la Vipère, was still there. My old lab was still functioning 25 years later, and it was still called the Viper pit. In 1996, I was at a medical physics meeting in Vancouver and happened to stumble across this fellow, Aaron Fenster, who was the director of the imaging program in London at the Robarts Research Institute. And he asked me if I would be keen to come to London to help them establish an image-guided surgery program there. And so I'd been in Montreal for almost 20 years. We've been through 2 referendums where Quebec was deciding whether to separate from Canada or not. And this became a topic of discussions. Are we still online?
Yep.
Okay. This became the topic of discussions in any social scenario you would encounter. So after 20 years of this, we thought, let's get out of it. Let's go to a different place. And so we ended up at the Robarts in 1997. This is our institute building, which is on the campus of the University of Western Ontario, now known as Western University, and literally connected directly to the hospital. So if you go to the end of Robarts, turn right, you get into the hospital, turn left, you get into medical school. So we have this ideal situation between the clinical practitioners on one side and the clinical researchers on the other side. And we have this environment where we accept people from engineering, physics, biomedical engineering, science, just about any discipline. We all work together on problems of interest. So by the time I arrived in London, the Viper program had become rather unwieldy. You'd fix something over here and something else over here would break. So we decided to go back to square one and build the ASP program. When one of my students was talking about this at a conference, someone said, "David, what does ASP stand for?" And without missing a beat, he said, "Acronym still pending." It was, of course, a continuation of Viper, but and so we developed this platform into a quite sophisticated program that allowed neurosurgeons to record both the effect of stimulating various parts of the brain and to record what happens when you stimulate parts of the brain. So, for example, stimulation in some part of the brain might cause the patient to hear music, might cause them to have tingling in their fingers. And these signs will help the surgeon target part of the brain that needs to be stimulated. for the treatment of Parkinson's disease, for example. So this so-called monkey man interface, which allowed them to very, very easily record exactly where electrodes were going and what was happening when they stimulated those electrodes, allowed them to build up a database over hundreds of patients. So when a new patient came along, they could interrogate that database and bring information from that database to the individual patient's plan. So multiple patients, every patient has one of these little dots that describe what happened when an electrode was at a particular place. All of these images have been normalized into a single space, and those of you who are in neuroimaging know about the MNI space, and so we all registered these to MNI space. And this allowed, when a new patient came along, for all of the data from previous patients to be brought into the same space as the new patient, and this could help the surgeon precisely target the region that is most likely to have an effect, rather than having to probe multiple regions and basically interrogate the patient. What are you feeling now? What's happening now? What's happening now? They've got all this information from multiple patients from hundreds of previous cases. So we showed that we could actually go to the correct location based on these data much more accurately than we could with just having the individual patient's data.
Is it pretty robust for all the net? I mean, if you get someone who comes in with their brain anatomy is not quite, you know, how extreme can it be in terms of?
So if there's a tumor that is really pushing the brain, then this system would not deal with it.
Yeah.
I mean, today's we could probably make those changes, but this, to the extent that one patient's anatomy could be matched to another patient's anatomy through a nonlinear walk, that to that extent, yes, it was robust. So one of the things that we got involved with quite a number of years ago now was trying to see more with MRI. We know that MRI images are comprise elements of T1 and T2 and proton density. But even with T1 weighted, T2 weighted, proton density weighted images, it's very difficult to see these deep brain structures clearly. And it's also very difficult, although not impossible, to make a raw T1 scan and a raw T2 scan in a reasonable time. So one of my students, Sean Dione, does that name ring a bell?
Rings a bell. Yeah.
He developed these algorithms called DESPOT 1 and DESPOT 2, standing for driven equilibrium of single pulse observation of T1 and T2. So this allowed multiple very fast image acquisitions with isotropic voxels, only taking 17 minutes of scan time, but then post-processing these images to allow us to get real T1 maps and real T2 maps. And because T1 and T2 weighted maps have a combination of T1 and T2 and proton density all mixed up together, it was very difficult to isolate certain structures. But now that we had T1 and T2 maps, we could be much more precise at what we're trying to see. And so we showed that using T1 and T2 images instead of T1 weighted and T2 weighted images, we could automatically segment these deep brain structures that we couldn't see before. So this is automatic segmentation of the thalamus on 4 different patients. The only input was seeding points where you thought the centroids of these regions might be. Then it would use an algorithm to automatically segment these into different regions. And you can see the strong degree of consistency between these different patients after this algorithm has been able to segment these different structures. So this was a huge advantage of being able to target one of these structures over another. But the real advances in MRI have come even more recently with a more quantitative set of data that the MR scanner can produce. In addition to the T1 and T2 values, we've got these diffusion weighted parameters that talk about how protons are diffusing in various directions in each voxel. And by using these, of course, we can build up three-dimensional maps of the nerve fibers in the brain. Also, we can use these multiparametric data to predict the cellular structure within the brain. So by using either deep learning or singular support the vector machines, using these multi-parametric data, we can show that certain regions of the brain have low cellular density or higher cellular density, for example. So this allows us to isolate regions in the brain that might be generating epileptic seizures, for example, and much more precisely identify which regions of the brain that need to be excised during epilepsy surgery. I'd been working on brain imaging and image-guided brain surgery for quite a while in Montreal Neuro, and then we were visited by some cardiac surgeons who had just taken delivery of a Da Vinci robot to perform heart surgery. One of the big problems with performing heart surgery with a robot is to be able to place the robotic ports between the ribs in exactly the right places so that you can easily access the vessels that you want to access. In this case, we want to access this vessel to perform an anastomosis of a blocked vessel, for example. And so we would look at the image prior to, look at the vascular structure prior to the surgical procedure. But once the patient gets in the operating room and has his chest pumped up with nitrogen to give the surgeon space to work, the heart shifts. So the previous image is not going to be much use. But by using transesophageal echography, which is an ultrasound transducer placed down the thorax and looking at the lung, looking at the heart, we can see how much movement there is after this insufflation has occurred. So we can tell how much the vessels have moved. And so we can build that into our algorithm. And you can see in this diagram, the green vessel is the vessel position of the vessel before insufflation. The red vessel is after insufflation. And we can use that information to get precisely to that targeted point. Another example of the work in cardiac surgery that we were doing was with respect to minimally invasive mitral valve repair. My surgical colleagues were very keen to provide a minimally invasive procedure to repair mitral valves rather than having to open the chest up, place the heart on a heart-lung machine, which means place the body on a heart-lung machine, which means you arrest the heart and the patient's blood supply is then being oxygenated by an external device. They said they wanted an MRI image of the heart, of the beating heart, registered to intraoperative ultrasound during surgery. So we had a couple of PhD students working on these projects, and we did it in 3D and stereo, and you can see these surgeons performing the procedure while looking at this image in 3D. So we thought, we've done a wonderful job with this, but after their experience, they sort of came up and said, I really don't know what I'm looking at. There's far too much information there for me to deal with. And you can imagine a heart surgeon during a cardiac procedure, he's already at this cognitive threshold, so he doesn't want more and more information being thrown at him. So we went back to the drawing board and tried to decide not what they wanted, but what they needed. And that's a good question for all of you when working with clinicians. Try to discern exactly what they need, because they'll have a different impression of what they want. But you have to iteratively talk with them for a long time to understand exactly what they need, with all of these other considerations involved as well. So the particular procedure that we looked at in detail was one that would repair a flailing mitral valve. The task here was to navigate a very simple instrument through the chest wall, through the apex of the heart, into the mitral valve annulus, as that little cartoon showed. And the typical way of doing this was to use two ultrasound images. These are cross-plane images, so you can imagine the transducer in behind the heart having two beams, one like that, one 90 degrees to it, but shown to the surgeon as being side by side. So that immediately provides a cognitive dissonance, because these images are not actually side by side. One's rotated with respect to the other. But this is what they had. And so we had 6 experienced cardiac surgeons performing this procedure just to get this probe into the mitral valve annulus. And we would track, using magnetic tracking technology, we would track the tip of this instrument as they were getting from the apex of the heart into the mitral valve annulus. Sounds like a pretty simple task. But when we analyzed all of these trajectories, we got something that looked like this. A real spaghetti, mess of spaghetti. The only thing that tells you is basically what the shape of the left ventricle is. You can see in some cases they actually went up through the wrong annulus, went up through the aortic annulus as well. So we redeveloped the interface and showed the surgeon the image that you see on the right, which showed a bullseye image that you see on the right, and an image looking perpendicular to that. So that this image shows how far away they are. This image shows how far away off the target they are. We had tracking technology built into the ultrasound scanner and into the tool. And when we did this, we ended up with a trajectory that looked like one you see here. So they went straight into the right place immediately. And this was 4 times faster for the procedure and 40 times safer in terms of the number of times the tip of the tool would go somewhere within the heart that we didn't want it to go. We also embedded a little ultrasound transducer inside that instrument so that the instrument itself could see the flailing leaflet, know exactly where it was, to bite down onto it. And inside this tool was a little crochet hook type of device that threads a thread through the leaflet, pulls it down, and then ties it on the heart wall. So this also demonstrates the difference between 2 very important phases of any image-guided procedure. One is navigation, getting to the target safely. And the other is positioning, putting the therapeutic instrument on the target in a precise manner. And many image-guided procedures can benefit by being broken down into these 2 phases, which can be quite different and may need different imaging modalities to achieve. On the road to this work in the cardiac field, we had done a number of in vivo pig studies, and those studies I showed you in the previous slide were all done on a pig. But pig studies are very, very expensive. They're logistically difficult. They're time consuming, and the pig doesn't always behave itself in the operating room. Pigs don't like their hearts being probed, and sometimes they'll die before you get the experiment done. So we ended up building just go back. Okay, oops, something's going to hammer me here. We built this heart valve simulator, heart valve motion simulator, which in this version shows the left ventricle contracts. At the end of that plane is a heart valve that can either be a generic heart valve or can be a patient-specific heart valve that we've acquired from preoperative ultrasound imaging that we can then make into a very realistic heart valve made from silicone. And the reason for doing this is that if a surgeon wants to practice a number of different scenarios for a particular pathology on a particular patient, he or she can take the images from the patient prior to surgery, convert them into a very realistic model, put them into this simulator to see what the behavior of that diseased heart valve is going to look like, and then perform a procedure that will correct it. But he has a choice from a number of procedures, and one procedure may not be best for every patient. So you can perform the procedure, put it into the simulator, and see immediately how that procedure is going to affect the blood flow. Instead of, in other words, does it stop all the blood flowing backwards, or does sometimes it flow backwards? And so they can customize their procedure for the individual patient using this sort of technique. So that's a bit of a whirlwind tour of what I've been up to over the past 50 years. My lab in London is called the VAST Lab, and it's been involved in many, many different image-guided interventions over the past 25 years in London. And although I'm nominally retired, I still wander into the lab to see what the students are doing. And we've just installed a brand new experimental operating room in the Robarts Research Institute that has CT, multiple robotic systems, multiple very, very advanced optical imaging systems, so that we can use this as a real-life prototype operating room for the development of new high-tech image-guided surgical procedures. So just some final thoughts. Don't get too discouraged if you think you've been scooped. Would have been easy for me to have just quit the whole CT business and moved on to something else. And also, experts are not always right, so don't necessarily just take one person's opinion for something. Talk to many people. When you are faced with choices on your career pathway, evaluate the different options and then go for one of them. Embrace it. Never look back. Never go and say, what if? Do your best on the path you've chosen, and you do extremely well. When you become professors, supervisors, give your students freedom to express themselves too. You'll be totally amazed at where they may take you. Finally, you never know where a stroll in Fourier space will lead you.